Hello everyone. In this video, we are going to learn a reaction that's specific to terminal alkynes. Okay, so this is a reaction of terminal alkynes. This is from section 9.10 in the textbook, okay? And this reaction is called an alkylation. Of terminal alkynes. So terminal, again, just to review, refresh your memories, this is when the triple bond is at the end of a carbon chain, okay? So that means we are talking about molecules like this, where we have a triple bond at the end of a carbon chain and then realize that this carbon here that has a hydrogen on it. And so this chemistry is basically the chemistry of this carbon. Okay, what can we do at that carbon? That is what we're going to talk about. So those are terminal alkynes, and we will not be discussing, okay, we are not discussing internal alkynes. This is an internal alkyne. We've seen that before. So we're not discussing those internal alkynes. We are discussing terminal alkynes. Okay. Now, terminal alkynes, they basically present a very unique opportunity in terms of doing reactions. Okay, and that's because this alkyne, okay, this alkyne, the pKa of this alkyne is about, this hydrogen is acidic, so the pKa is about 25. Okay, the pKa of that this hydrogen, okay, not that carbon, the pKa is for this hydrogen, that's about 25. And you can imagine this because once we deprotonate, so if this is the acid, then the conjugate base is going to be that. This is the conjugate base of this terminal alkyne. And this conjugate base is a negative charge on an sp hybridized carbon. This carbon is sp hybridized, which is kind of electronegative compared to an sp3 or an sp2 hybridized carbon, and it can hold that negative charge better. So it is sort of like relatively it is stabilized compared to other carbon-based anions, okay? And so because of that, what we can do is this hydrogen can be deprotonated using any base, any strong base, okay? It can be deprotonated using any strong base. Now, what is a strong base? Let's just review quickly some of chapter 3, okay, to get a feel for, okay, what sort of a base can we use here? Okay, so let's say if I react this terminal alkyne with sodium methoxide, we know that this is a strong base. It's also a strong nucleophile, but in this particular context, we're using this as a base. So if you do this reaction, going back to chapter 3, the base is going to come deprotonate. The electrons here go to that carbon, okay, electrons from that bond go to the carbon. And what this would give me is the conjugate base of this alkyne, which is going to be a negative charge on that carbon, plus, and this sodium will be with this, plus this would give me methanol. pKa of an alkyne terminal alkyne is around 25. pKa of an alcohol is about 16. And so what that means is our strong acid, or the stronger acid, relatively stronger acid, is on the product side. So this reaction is actually favored in the backward direction. That means when you have this ion and this conjugate base, this has a name. This is called an acetylide ion. Okay, the carbon with the negative charge, the sp hybridized carbon with the negative charge is called an acetylide ion. So when you have an acetylide ion and an alcohol, that reaction is more likely to give you the alkyne plus the conjugate base of the alcohol. So this is preferred in the backward direction because our stronger acid is on the product side. But instead, okay, let me get rid of all of this. Instead, if we had a terminal alkyne and we react this with sodium amide, let's say, and NH2, okay? This is sodium amide. You can also call it amide, okay? Either way, sodium amide or amide, if you do that, that's a base, comes and deprotonates. That nitrogen has a two lone pairs on it, comes and deprotonates the alkyne. Electrons here go to that carbon. So pay attention to my electron push. I'm using the bond here, moving those electrons to that carbon, the terminal carbon over there. And this would again give us the acetylide ion along with the sodium, plus it's going to give us ammonia. pKa here is about 25, and pKa of ammonia is around 36. And now if you look at it, our lower pKa is on the reactant side. That means this reaction is favored in the forward direction. That means a strong base. So you can basically look at a pKa table or a pKb table and predict which base is strong enough to deprotonate an acetylide ion, using the pKa stuff, using the quantitative analysis of acid-base reactions that we learned in chapter 3. So you basically combine those two and you can predict which base is strong enough to do it. Okay. So what that means is we can use sodium amide. I think this is a good example, the most common example that's used. You can use sodium amide as a base to deprotonate an alkyne. This is a terminal alkyne. Again, remember that this is a reaction of terminal alkyne, and you can generate an acetylide ion. You can generate an acetylide ion. Now, when you look at acetylide ion, this is a carbon with a negative charge to it. So what can we call this now? What you should realize is this acetylide ion can behave as a strong nucleophile, and it can also behave as a strong base. So it's both a strong nucleophile and strong base. But this alkylation reaction that we're discussing here, that uses acetylide ion as a strong nucleophile. So it basically uses the nucleophilic properties of the acetylide ion, because it's a strong nucleophile. So essentially what I can do is I can take a terminal alkyne, use sodium amide to deprotonate it to get the acetylide ion. And once I have the acetylide ion, I can take any acetylide ion. Okay, so this is an acetylide ion. I can take it, and this is a strong nucleophile and a strong base. So if I have this acetylide ion, and if I react it with a primary alkyl halide. So we have a strong nucleophile, we have a primary alkyl halide. So what sort of a reaction should I expect? This is going to give me an SN2 reaction. So the acetylide is going to go and attack that alpha carbon. Okay, so it takes us back to chapter 7 in some sense, attacks the alpha carbon. X gets kicked out, that's our leaving group. And what we're going to get is we will have that plus R prime, where that's our alpha carbon. That's where the attack happened. So what this reaction allows us to do is convert a terminal alkyne. That's where we started here. Okay, we started with a terminal alkyne, and through or via an acetylide ion, we can convert a terminal alkyne into an internal alkyne. Okay, so we can basically do this reaction. So that's the alkylation of terminal alkyne. So let's look at a specific example now. How this would work, so let's look at an example and we'll try to see it both forward and backward. So let's say we have an alkyne, which is CH3, that, okay, this is the alkyne we have, and what we're going to do is we're going to react this first with sodium amide, and second, we're going to react this alkyne with methyl bromide. That is what we're doing here, okay? So what would happen is, that's what we need to predict, okay? What would be the product, okay? So if you look at it, this is a terminal alkyne, so there's that hydrogen over there. So sodium amide is going to deprotonate this alkyne. That would give us methyl, or the acetylide ion here. Okay, it will give us the acetylide, and I'm not working through the entire mechanism here. I'm just trying to show you the sort of intermediates that would form. So when this alkyne gets deprotonated, I will get this acetylide ion. And now that's the first step. So in the second step, this acetylide ion goes and attacks the methyl group, kicks out the bromine. So that means the product that we are going to get here is going to be this, where we've added a methyl group to this alkyne. So we started with a terminal alkyne, and now we've made an internal alkyne. And by choosing our alkyl halide, we can put whatever alkyl group that we want to put here. Okay, that's up to us. Another example that you might want to see is, let's say if I start with the simplest alkyne possible. So there are two carbons here. They both have hydrogens on them. And on this, if I did 1 sodium amide, 2 methyl bromide. I'm just randomly picking some examples to show you guys this, okay? 3 reacted with sodium amide again, and 4th reacted with ETBR, ethyl bromide. Okay, I think we went over this thing one time, but ETBR is ethyl bromide. What are we going to get here? Okay, so if you think about it, we have this alkyne, which has actually 2 acidic hydrogens. Okay, this is just the simplest alkyne. It has 2 acidic hydrogens. So when we do the sodium amide step, okay, after the first step, this comes and deprotonates. So this should give us an acetylide ion. Now this acetylide ion can go and attack the methyl group and kick out the bromine. You don't have to show it like this when you're working through a problem on a quiz or an exam. You might want to do it separately if you want to, but if you just want to write your product, well, the work is always good, I think. It's always good to show your work because then you get partial credit. But if you just write a product and if it's wrong, it's wrong, okay? I cannot give you any partial credit over there. So this would attack that. So essentially what that means is after this second step, I'm going to write it here. After the second step, what I would have is triple bond with a methyl connected to it. Okay, we are at the second step now. So this is from here. And now in the third step, we have more sodium amide. So the amide can go and deprotonate on the other side now. Let's go over there. So this is going to give us another acetylide ion now. That's based on a propyne. So we get a new acetylide ion. And now that acetylide ion can come and attack the ethyl group, kick out the bromine. So that means finally what we're going to get is we're going to get a product where we have a methyl on one side, we have an alkyne, and then we have an ethyl on the other side. So now we've added alkyl groups to both ends of that of this simplest alkyne. So we can do it sequentially and then add groups to the alkyne. Now I cannot do anything more to this because this does not have any of the acidic hydrogens now. Okay, this is an internal alkyne, so there's nothing else that I can do on this. Okay, so that's the reaction here. So this is an alkylation of a terminal alkyne. Okay, alkylation of terminal alkyne. It converts a terminal alkyne. So what it does is it converts a terminal alkyne to an internal alkyne. Okay, it converts a terminal alkyne into an internal alkyne. It's from section 9.10. Bye.